So I'd like to introduce the moderator of the next session, which is going to focus on systems. So it is Sadique SHEIK from SynSense, who coincidentally is also going to be the first speaker of this session. So Sadique, the floor is yours.
Thanks a lot, Charlotte. I hope everyone is back and refreshed from the break. My name is Sadique. I work at SynSense, and I'll kick off this session with some of our experiences of deploying spiking neural networks for low-power real-time inference. We'll focus on neuromorphic smart sensors for today's talk. That is, sensors plus processors in the same system on chip. The expectation from these smart sensors is that they provide highly informative, low bandwidth output. So this is exactly the continuation of the previous talk. If we do have this, then this will enable us to do things like smart condition detection, smart wake up, continuous monitoring at ultra low power and ultra low latency. So that's what we do at SynSense. We specialize in developing neuromorphic smart sensors. We are a spin-off from the University of Zurich and ETH Zurich, and we currently have offices in Zurich and China. At the moment, we develop three chip families. The first is the DynapCNN. This is a fully asynchronous, event-driven, multi-layer spiking convolutional neural network processor. The second is SPEC. This is a fusion of DynapCNN technology with dynamic vision sensor technology to produce an extremely compact and efficient vision processing SoC. Lastly, we have Xylo, an ultra low power and compact SNN processor that is focused towards low dimensional natural signal processing. In order to work with these devices, we also develop and publish software libraries. The first is Samna for low-level interaction and fast data processing and visualization of event data. Then we have Rockpool and Synapse for development of spiking neural network models and porting them to Xylo and SPEC. Finally, we have Tonic, which is designed for data handling and pre-processing of spike data. These are all publicly available libraries and published on PyPy. Here is a super high-level overview of the development and deployment pipeline for our developers. I'll skip this slide in the interest of time, but point out that essentially you have very few lines of code to go from your model that you know works to deploying that onto our chips using essentially the PyTorch API, which is to say your model.to, the device name, and that's it. So the tooling pipeline enables us to rapidly prototype several applications. Some of those are shown here. In the interest of time, I'll actually focus on only one of these for today's talk. And that would be object detection and classification. This is a very classical computer vision task. Standard object detection pipelines like YOLO or faster RCNN are very popular and work on image frames. But they're relatively large and complex for tinyML applications. So we here take a slightly different approach inspired by neuromorphic principles. So the first thing is we actually are working with continuous event streams from DVS sensors, and we'd like to avoid any kind of frame buffering and frame building. So what we do is we solve this problem in parts. We first try and answer the where question. And we do this using event-based object detection algorithms. Once this problem is addressed, then we are only forwarding the relevant events to a miniature classification network to answer the what. We apply this approach to a toy demonstration here. You'll see two toy cars rolling under an event-based vision sensor that is mounted on a tripod. the cars have to be detected and classified in real time. The bottom left corner of the screen shows what the sensor is seeing. The rightmost corner shows what the prediction of the network is. The peak power of the classification network is a mere 8 milliwatts. And that is the peak power. If you assume 20% activity sparsity, we're looking at approximately 1.5 milliwatts at an effective inference rate of more than 150 hertz. I say effective inference rate. This corresponds actually to a latency of 6 milliseconds from the object's onset into the scene. This is extremely fast, and probably it's hard for you to follow this video. So here's a slow-mo of what's going on. This is what the camera sees to your left. Then the objects are identified, and the identified objects are seen in the center panel. And the classification result is seen on the right. All right, so I then want to go over one application on Xylo, and this would be an audio-based ambience scene classification task. For this particular application, the raw audio is passed through a filter bank to generate spikes. These spikes are fed through a multi-layer spiking neural network. So we deploy this on Xylo. You'll see a few audio clips being played. The output of the network will be displayed here. On top, you have the raw audio waveform. And these are the prediction labels. The network consumes a dynamic power of roughly 93 microwatts and a median latency of about 100 milliseconds from the time of. Okay, I'm going to pause this video so I'm actually audible. So that's all I wanted to show in terms of applications. So you have ultra low power audio classification on Xylo and ultra low power vision processing on SPEC. With that, I'd like to conclude my talk. I hope I was able to give you a feeling for the types of applications that could benefit from neuromorphic technology and a flavor for the devices from SynSense. Here, there are a few references if you want to know more about the types of things we're working on. I also wanted to advertise 2 talks from my colleagues at the tinyML EMEA in Cyprus on the 10th and 11th of October, where they will go a lot deeper into the details of vision processing and low power signal processing. With that, I'd like to thank you all, and I'm happy to take questions.
Thank you so much for the great talk. I see no questions in the Q&A so far, so I will have one. SynSense is one of the very few companies that has investigated both analog and digital accelerators. So I would like to have your insight as to what are the best use cases for each.
Yeah, so I'd like to start with the fact that both the chips that I showed today happen to be digital. One of the reasons for the choice of digital, and this I can speak for most of the other companies here perhaps, is it just enables scaling a lot easier. But digital also means that you are running a clock. So if the scale of your application is not large, if you do not have hundreds and thousands of neurons that you need to be deployed, our belief is that you can operate in analog and you'll benefit from the compactness of it. On the other hand, if you do want a very large scale network deployed especially if you're training things with deep learning, then you want everything to be reasonably precise, and there you would benefit from sticking to digital. That would be my 2 cents.
Sounds great. Yes, I will encourage the audience, if there's any further question, to continue posting in the Q&A, and then Sadique will handle the replies asynchronously. So the floor is yours again for the next talks.
Thanks a lot, Charlotte. All right, so next we have Jae-sun SEO. He's from ASU, and he'll speak about fully spike-based architecture with front-end dynamic vision sensors and back-end spiking neural networks. So perfect follow-up from my talk.
Yeah, thank you very much for the introduction. Hope everybody can hear me well. So I'm Jae-sun SEO from ASU, and it's great to have a chance to talk at this neuromorphic workshop. So wanted to first start off my talk that, neuromorphic is certainly an interesting and emerging field, especially on the algorithm and hardware side, but it might not be for everything, especially there are many inputs like natural images, raw speech, and other many data types that are not necessarily all in spiking format. And if we want to pursue that with some spiking neural networks, then we need to convert some of these real values to spikes using a converter, which by itself adds energy. But instead, as mentioned in several talks earlier today, if there are some of the front-end sensors that has output directly in the spike format, then it can be more naturally connected and directly connected to the back-end spiking neural networks and accelerators. So dynamic vision sensor, or DVS, is a very well-known event-based vision sensor that sends spikes only when event happens at the pixel level. For example, the pixel intensity changes in the positive or negative direction. And because, we don't really send out redundant kind of background kind of pixel information every time, it has been prototyped in academia, industry, as we know. Also saw a talk from Profizi. And on the other side, on the training with the spike format, we also saw some talks in the morning about some resemblance of the spiking neural network and the binary formation of the spike. And also in the machine learning literature, there are these binary neural networks that have been successfully trained. If we just change some of these neuron activations represented by +1 and -1 in BNNs into +1 and 0 in typical SNNs, then we can have some of these backprop-based techniques and technologies directly applied to BNNs, to SNNs with some of the customization. So that's one of the works that we have also been keep investigating, to do discrete time SNN with continuous integration to target some of these dynamic and temporal inputs such as DVS spikes. So we had proposed in several years back by CAS, SNN training framework with multiple time steps, where the main difference between a conventional neuron model and the spiking neuron model that has been proposed is to continuously integrate the member potential over time. And to do that, we have to have this time or temporal factor in the overall tensor format, so that we have the batch and neurons as well as time. But it's relatively simpler than RNNs because, all the time steps have the same importance. We don't have to really train, some of the weights between which previous time step we're integrating. So that's how the typical memory potential integration happens. And it's worth noting that, nowadays there are several spiking neuromorphic data sets that, SNN algorithms can be benchmarked against. So typically, some of them early ones in front of, put a DVS camera in front of static images and kind of arbitrarily move the DVS to generate spikes or events. Or obviously DVS can capture some of these dynamic events like hand clapping, or we can put, a DVS in a car and do a, self-drive and have kind of a objects and spike come in like this. So there has been some of these NCalTech 101 and MNIST DFAR10 in a DVS format, this IBM gesture data set, and most recently this Profizi much larger automotive Gen 1 data set. So in one of our early works, we benchmarked this NMNIST. So with this kind of DVS outputs coming out, have to classify which digit it is, and because, the camera is moving up or down or in different directions, we can also recognize which directions it's moving. So we can try to, train these SNNs to classify these different objectives, and you can see pretty high accuracy was achieved. And we also went ahead and designed a preliminary accelerator in TSMC 28nm CMOS technology with a very large weight memory and an all digital synchronous, but, heavily clock gated flow. So we're trying to, in this preliminary work, we're showing that combination of the event-based vision sensors, SNN training algorithm, and the sparsity-aware hardware design can result in very low energy consumption from sensor to the backend for the classification task that we're targeting. More recently, I want to point out that, for example, like CFAR 10 DBS is one of the data sets that is benchmarked a lot. And I, put together some of the data points of recent algorithms that has been presented in various venues, for example, Frontier Neuroscience, and also many machine learning conferences such as ICLR, NeurIPS, and CVPR. And you can see that the CFAR 10 DBS accuracy is keep going up while, try to use less model size in the upper left direction. And on the object detection side, Profeezi put out this automotive Gen 1 data set using, for example, MobileNet V2 and, put it on a car. It can kind of detect some of these objects in real time like this. But still, millions of weights you can see, and the model size are in the megabyte range, and a lot of the algorithm works are still in floating point precision. So if we really want to map this onto, some front-end device together with the accelerator, then that becomes a challenge for the footprint as well as power. On the other side, similar to kind of the main machine learning kind of development, we saw that for ImageNet, there has been an explosion in the accuracy, and that actually, led to many custom accelerator designs. And I can actually foresee that now, back in the day, some of these SNN algorithm accuracy was not that great, but due to many of these researchers keep pushing it, we're seeing higher and higher accuracy. And I can see, higher object detection MAP, for example, will come for the Profeezi data set in the future. And that can certainly push the custom hardware design too. And I can see that, including our group and many other groups, there will be more custom SoC also from startup companies that will be developed. So in one of this work from AICAS 2021, they trained the Profeezi Gen 1 data set, customized the algorithm with that, and then also customized the hardware, resulting in some low power consumption. So to quickly summarize, I try to point out that back propagation-based SNN training algorithms, together with the hardware efficient, spiking neuron models, could be a path to efficiently train SNN-based algorithms that are mated with front-end DBS, and then the back-end corresponding SNN accelerator can certainly try to exploit kind of the firing sparsity from the front end to the back end until the output comes out. So this, DBS plus SNN, we're combining a high resolution sensor with sparse outputs only depending on the actual event or activity. Nowadays, a lot of these SNN algorithms are pushed to high accuracy, supposedly with, less parameters as well. And then we can combine that with the low power hardware that fully exploits the sparsity. And I would like to acknowledge my collaborators, students, and my sponsors here. Thank you very much.
Thanks a lot, Jae-sun. I haven't seen any active questions, but I have several. But I'll ask you one. So one of the things with deploying these classifiers on hardware is the amount of memory required, not only for the parameters, but also the states.
Yeah.
And oftentimes that ends up being prohibitively large as the size of the networks grow. What has been your insight into this when you're trying to address problems that are actually rather complex with ImageNet or CFAR even is not a tiny network? Right.
Yeah, I think that's the point. And I think only, one of the specific challenges that some of these accelerators are facing, as you exactly said, I think the memory potential values have to be stored for the kind of, most of the entire network, because we're keep, updating them over time. So I think that's why some of these, algorithm and hardware co-design certainly has to take place. And it really depends on the application, the form factor that needs to achieve, and the accuracy that needs to be achieved for the given task. So we can try to certainly, trade off some of the model size and try to emphasize on, now that we really understand some of the member potentials actually can limit the, memory and the hardware needed, then, try to reduce the number of active neurons in the actual SNN algorithm design. So I think these have to be pushed down really, to have not only less parameters, but also kind of overall less storage required for the member potential. And then, low precision, how many bits really we need for each of the member potential instead of using, naively floating point and kind of aggressively pushing it. And then how does accuracy trade off with that, I think are all kind of active areas of research.
Great. Thanks a lot for that answer, Jae-sun. I do not see any other questions, so thanks a lot again.
Okay, thank you very much.
Thank you, Jae-sun. So our next speaker is Chetan Singh THAKUR. He's from IISc, and he'll be talking about tinyML in-filter computing with neuromorphic cochlea.
Let me get started. Hello, everyone. I'm Chetan Singh THAKUR, assistant professor at IISc. Today, I'll be talking about tinyML in-filter computing using neuromorphic cochlea. So let me give a brief overview of tinyML activities, what we do in our lab. We have multiple tinyML solutions based on power, performance in area, and time to market. In fact, we have recently built this analog Aryabhat chip, which stands for analog reconfigurable and technology and bias scalable hardware for AI tasks. Another is digital systems, because people are arguing about various technology, analog or digital, what is better than others and so on. So we have digital solution as well, because scalable, as Sadique was pointing out, and the name is Raman, which stands for reconfigurable and sparse ML accelerator for deep neural networks. Here we are exploiting weight and activation sparsity, which we just pointed out. And some are hybrid architecture where we use novel emerging devices like memory stars and so on. But today's talk will focus on tinyML on microcontroller with constrained resources. Mainly we will be using Cortex M4 devices here, where we explore various sensing modalities such as acoustic, vision, IMU, and mmWave radar. Today's talk mainly focus on acoustic sensing modality here. So what tinyML can benefit from neuromorphic system, right? So the first is in sensing computation. Several speakers have argued about that, or smart sensor, right? And biological sensory systems compress and send only relevant information, and roughly it compress around from 10 megabits to less than 50 bits per second, right? And so basically you are interested only relevant information here. Second, what we can learn from from neuromorphic system is ultra rapid processing, right? If you see, it takes roughly 100 millisecond latency to reach the visual information to visual IT area, which is roughly 10 layers from retina to IT area in the brain or in the cortex. That means one spike per layer for fast processing. So can we explore better information encoding, such as temporal encoding, which people have been arguing in the talk so far, right? And third is sparsity. And it's well known that brain uses sparse encoding for both sensing and computation, and at the same time, roughly 1% of the neurons are active, right? So can we use those kind of thing in our tinyML system, right? And the next is to achieve ultra low power. Can we use some of those neuromorphic principles, such as distributed architecture, asynchronous design, efficient encoding, and communication, right? Or analog mixed signal design. And we know, and finally, we know the brain is very good at learning with few data points, right? Can we use that? Can we use those kind of neuromorphic principles? So here in this, in today's talk, based on this last argument, learning with few data points, which we have been arguing here, and for deploying on the tinyML MCUs, we have chosen this support vector machine, which is the best candidate for tinyML application. However, conventional support vector machine has several drawbacks, and that's what we have came up with new formulation from support vector machine, and that's what I'm going to talk about that and how we have deployed it here. So if you see this in conventional support vector machine or SVM, the kernel has to be positive definite, which limits to use simple nonlinear primitives, right? And we cannot control the memory and computational constraints required by the tinyML system, which is generally the resource constraint devices. So to overcome this, we propose this novel template-based SVM, which solves this issue, and the kernel itself can be used as pre-processing stage, right? Which is in an important thing here to notice, right? Kernel can be used as a pre-processing or a feature extraction stage, which we exploited in our formulation. So if you see this, unlike a conventional acoustic pattern recognition task where the feature extraction is a separate stage and the classification are designed independently, right? So this here in our proposed architecture, we integrate the convolution and nonlinear filtering operation directly into the kernel of support vector machine. We demonstrated this concept using Cochlea model, which we use our in-house built Neuromorphic Cochlea model as a feature extraction, as well as the kernel of the SVM. So here, instead of separate feature extraction and the classification, we merge both together, and that saves significant amount of memory constraint and resource uses. And also, let me give you another interesting thing about it. So if you see this memory footprint by the support vectors of this conventional SVM is determine the complexity of the problem, right? So you can't control the number of support vectors. And if you have limited memory constraints and the resource constraint, you can't just use any problem with SVM, right? So in this new formulation, we reported a mechanism to design SVM using arbitrary template function. Here it's a phi, within a fixed memory footprint. So P here you can define a priori based on whatever the constraints you have. So this is the detailed formulation which can be found in our paper, where this phi is our Cochlea filter banks with P filters. So we can choose how many number of filters you want based on the task or based on the memory and resource constraint. So that's the key here. So let me talk briefly about the cochlea. So cochlea is where the sound energy converts to mechanical energy and then to electrical energy with right impedance matching in the whole auditory pathway, right? So this cochlea contains a flexible membrane, the basilar membrane, which extracts the different frequency content of the incoming sound. And you have then outer hair cells, which is around 12,000 in number, which controls the gain of this filter bank dynamically, which enables to have almost like a 120 dB of dynamic range, which is huge if you compare with the existing engineering system. And then you have inner hair cell, which is around roughly 3,500 inner hair cells, which encode the velocity of the basilar membrane and generate the spike train, which goes to the auditory cortex and so on. And this is the gain plot of the cochlea model, which we have. And this is a digital cochlea model, which has both outer hair cells and inner hair cells. And that's why it is very flexible for deploying in MCU and FPGA and so on. And we have several works in the past, which we did deploying in various, all this deployment platform. And this faithfully replicates the biological counterparts. So this our current formulation supports any time series data, not only acoustic, but is such as you can use it for music or IMU data. We have built a couple of solutions with IMU data, which could be useful for industry applications, and ECG and EG, which could be useful for BC applications and so on, just by changing the center frequency of the filter bank, right? Because basically in all those applications, the feature extraction is nothing, but you want to extract the frequency content of the incoming signal, right? So thus it can be used for wide variety of application, not only ranging from healthcare to transportation to environment monitoring and so on, right? So there's the whole framework you can deploy for any other applications. So these are the different deployment platforms in MCU and FPGA, which we have deployed mainly for acoustic application today we are showing, but as I said, it's also for other applications. So here we deployed for AudioMoth, which has Cortex M4 MCU. You have a then very small tiny Seed Studio, which again has Cortex M4. Then we have the CC1352, which has very nice sensor control, and you can go literally low power here with the limited memory. And also we demonstrated with FPGA, so that if you want to have high performance and low power, this, as I said, right, this is a digital solution. The Cochlea is digital. We also deployed here, and the power number is very small, 8 milliwatts. And if you see these LUTs, those who are coming from digital background, they can appreciate the number of LUTs which is taking, and the flip-flops, which is around 1.5K and 2.8K, which is pretty small in terms of FPGA, and you can do a lot of stuff with this. And here, all this with 30 filter banks, which we used in the Cochlea for the application which we just pointed out. So these are the classification performance. Just to show you here we have demonstrated on various data sets. So here the key thing again I'm pointing out, we can fix the number of support vectors in our formulation based on memory and computational budget from the device, unlike traditional SVM. So here we fix 30 filter banks, which again act as a kernel and also feature extractor, and we achieve almost similar accuracy as traditional SVM, which has more support vectors. If you see the numbers, in sometime it is 113 and 86, and here we just with 30 filter banks or support vectors, you're able to achieve the similar accuracy. Here is a simple demo which we did on 1352 for microbat, ultra low power acoustic classification, which we deployed here at our institute, IISc, for bird detection. We deployed this whole solution using AudioMoth in India, in the Northeast area, in one of the national park, using this sensor network, which with AudioMoth and the LoRa connectivity, and so this is mainly for timber poaching, gunshot detection, and saw cutting, and so on. So this is the application with the whole system has been deployed with building a sensor networks. And thank you. This was the last slide. So
thanks a lot, Chetan.
Yeah, do we have time so I can share the video? Otherwise, it's fine.
We have a few questions, so maybe let's answer the questions.
Okay.
So the first question is, are there any drawbacks to the SVM approach that you presented compared to a standard approach?
So what we are saying, if you have given the memory constraint, this is the best you can do. If you choose the number of support vectors, this is the best you can do. You will find the maximum margin classifier given the constraint you have. So we are going bottom up based on the memory constraints and all the resource constraints.
So does that mean if you had infinite resources, you would match the standard?
But then probably you don't need, yeah. So even with this, if you see, it's almost like hardly we are losing any accuracy there for this kind of application.
I see. Okay, great. One last question about the power consumption that you reported 8 milliwatts. Is that the total power or just the dynamic power?
So this is the total power when we measured directly from VDD.
Great. Thank you very much, Chetan.
Yep.
That was a nice presentation. Okay, so then let's move on to our next speaker.
Okay, no problem.
We have Anil MANKAR from BrainChip, and he'll talk about combining neuromorphic design principles with modern learning algorithms. Stage is yours, Anil.
Anyway, my name is Anil MANKAR. I'm the Chief Development Officer and co-founder for BrainChip. Here, you have heard a lot about neuromorphic principles and machine learning and everything else. So we actually show a solution that combines all of those neuromorphic design principles with modern machine learning algorithms to give you the efficient edge AI devices, what can be done on the edge. Before I get into the product, a little bit about us. We are actually been using 15 years of AI architecture research. And what we are the worldwide leader in edge AI on-chip processing and learning. We are the first to commercialize neuromorphic IP platform and reference chip. And so our neuromorphic IP, which is completely digital, actually has been used by a few of our customers to embed that into their SoC. We have a deep pattern portfolio of neuromorphic implementation AI. And we are a multinational company with locations in Laguna Hills, Orange County, Southern California, Perth, Australia, France, Toulouse, France, and India. And we are financed through a public financing on Australian Stock Exchange. When you talk about focus on trying to do edge AI inference, you have to really choose a efficient architecture and do a balance of design and performance, which allows you to give a lot of architecture options and algorithmic options, and which of those you choose to make AI better for edge devices. So you can see that they are, of course, analog digital design, spintronics, low precision computation, at memory compute, in-memory compute, ferroelectric devices, SVM machine that you have heard about, systolic arrays. So lots of choices on hardware architecture, including event-based. And on the algorithms also, there are a lot of algorithms for CNN and DNS, SNN algorithms, transformer network, LSTM networks. Of course, for AI at the edge, you need learning. So there are different forms of learning, transfer learning, So what we did is we actually decided to make an efficient solution for edge AI, and we chose low precision compute and at memory compute and event-based. Those are the neuromorphic design principles. And on the algorithmic side, we saw that there are a lot of CNNs are pretty good at extracting some features, while spiking neural networks are very good for neuromorphic computation. And definitely we need to have a single shot learning or few shot learning and make the transfer learning efficient. So combining those things gives you the best of both worlds. I mean, we actually work with CNN, converting them to SNN and native SNN also. So let's see what the technology foundation gives you. So there are 6 principles. 2 of them are basically fully digital design and running conventional neural networks, and the other 4 are neuromorphic architecture and algorithms. So the choices we made give you material benefits for any edge device that includes BrainChip IP embedded into the SoC. So first thing is digital design. Now you can see that CMOS digital design, it allows you to scale the compute requirement for this kind of solution that you're doing. Fully digital design has been very mature for decades of research. We can go from 4 nanometer to 180 nanometer. We are process agnostic. All we need is memory and standard cell logic and all the software tools. So we take advantage of that. Second thing that you'll see is conventional CNNs have been pretty good. I mean, even though brain doesn't use backpropagation or floating point math, it does. CNNs are good at extracting features, and there are lots of people have invested a lot of time and effort in creating algorithms and deep learning CNNs with feature extraction. So we take advantage of that, but only the inference for those CNNs, we can convert those into SNN to run them on the AGI device. We actually maintain those features, and if the data is coming from a standard RGB camera or audio samples, we actually create spikes out of that, and the actual inference will happen in the event domain. Similarly, at memory compute allows us to get each of the NPU with a dedicated memory, so the memory movements is reduced. And event-based processing, we only have to process events when there are spikes. So the NPUs can compete with events, and run, of course, they run native SNN, so we work with camera like prophecy camera and other maybe cochleas. If there's a sensor that generates direct spikes, we take those. But if a sensor that generating some standard data, our IP will take that standard data and convert those into spikes. But all the inference happens in event domain. Typically, when you run a network, the network connectivity also can be mapped into our mesh network. So because we do event-based communication, so multi-layers of the network can be run in hardware. So that allows you don't really need a CPU to come in and interpret the results between layers. So all of that gives us low power advantage and low memory bandwidth and low memory requirement and low memory bandwidth. So that the last portion of that is learning. We actually, Professor Raj from Johns Hopkins talked about STDP learning, so I don't have to go into details of that, but we actually implement that in our hardware on chip, because we think that when you talk about intelligence comes from learning. Most of the CNNs are basically trained, and learning leads to knowledge, and knowledge leads to intelligence. So we need to have a learning on chip. So here is the architecture that you see. We talked about NPUs has in-memory compute. Multiple of those NPUs become nodes, and the nodes can communicate to each other through a mesh network. We go up to 1, 2, or 4 bit activation and weights. So we have a complete software environment which will take the standard CNN, your weights, you don't need to change anything. We convert those into SNN, and we also, of course, do native SNN with devices that generate spikes. One thing that you see is the way, because it's scalable, it's all digital, you can be in the sensor, like you can have a camera-based thing, which is a small AI hardware there that can really send a region of interest and infer metadata. So we can reduce the total data movement across and all the levels of system level solution. So what we are really saying is we need a paradigm shift when you think about you want to do AI inference on the edge. So edge is not something that is a smaller version of what you do in the cloud. You have to really think about redesigning from ground up. And the paradigm shift really requires that we better start thinking neuromorphic design, which is the future. But our IP actually solves today's problem, which is CNN converted to SNN, and ready for the same hardware will do neuromorphic computation with neuromorphic sensors. So that gives you extremely low power at the end integration. But this is a chart that was shown earlier, which you cannot keep throwing more compute and more memory at this problem. And once you go into neuromorphic, the single shot learning, on-chip learning, adaptability to the environment actually helps. And now we can actually take the temporal component of the information that's coming in the spiking domain also. So in a standard CNN, temporal component is lost, but by going to neuromorphic architecture and keeping maintenance, keeping compatibility with old CNN while we're waiting for the future is a unique solution that we have. That should be my talk. I would like to take some questions.
Thanks a lot, Anil.
Yeah.
You have 2 questions, so I'll start with the first one. This is a tough one and is not just on you. Is there an example of an application running on neuromorphic hardware that exceeds the performance of standard AI acceleration hardware? So please speak.
It depends on what being the performance. Is it performance? Is it just frame per second, or is it at a solution at certain power, right? So you'll definitely have the way we have designed it. You can definitely do the same amount of computation that you'll need for any CNN application. So the inference, how many MAC operations you have to do, because we do those in neuromorphic digital design, it will all be low power because you can actually you automatically avoid multiplication by zeros in weights and also in activation. Typically, you can avoid multiplication by 0 in weights, but not in activation because it changes every frame. So yes, every solution that can be run on a standard deep learning accelerator will run on neuromorphic hardware. It will be low power, given the same technology and same clock speed and whatever is everything being same. So yes, we've seen that, and we actually also directly work with cameras like Prophecy and Oakley that will see that we can learn on the device and learn from incoming spike, and really STDP learning that happens on the device that we can learn with few samples.
Thank you. The second question is, when you run conventional CNNs, are they still translated to event-based?
Yes, they are. Yeah, they are, because what we have a software called MetaTF. MetaTF means after TensorFlow, you come into our domain. Now you can actually quantize it to 1, 2, or 4 bits, and you do not have to change your network what you were using before. Only thing now, the inference calculation and computation happen in spiking domain. So we have, our IP comes with what we call the data to event converter, and it will take the data, whether it's audio samples or RGB frames. It will create spikes out of that, and all the computation happens in the event domain. And if the network fits on our IP that's available, it will run completely independent of the CPU.
Great. Thanks a lot, Anil.
You bet.
We move on to the next speaker, Davide SCARAMUZZA, this time from University of Zurich and ETH Zurich. And he'll talk about autonomous agile drones.
Yeah.
Nice meeting you all virtually. So I'm going to talk about event cameras for safer robotics. So first, a quick recap on event cameras. So event cameras are vision sensors that measure only motion in the scene, and they measure this continuously. So they actually have a very low latency and very low power consumption, and also almost no motion blur, which is actually really ideal for high-speed robotic and computer vision applications. The problem is that you cannot apply traditional vision algorithms. So for the past N years, the community has been working on this problem, trying to basically adapt former computer vision algorithms to this continuous event stream. And here I would like to highlight some of the results that we achieved in my group. For example, to make robots safer, we used event cameras to allow a drone, for example, dodging balls thrown by people to it while the drone was actually translating. And we showed that using an event camera, you can dodge objects with the latencies that are around 3.5 milliseconds with relative speeds up to 10 meters per second. Also, in robotics, what is also very important is the ability of a robot to continuously estimate its own state, meaning the position, velocity, and the orientation. The problem is that if you do this with standard cameras, in high-speed applications, we will certainly suffer from motion blur. For example, what you see in this video on the top right is the onboard camera during a motion, like a lasso motion, where the camera is being spinned as a cowboy by hand through the USB cable. And you can see that basically most of the pixels are washed out or motion blurred. On the other side, event cameras are not affected by motion blur. And so we were actually able to design algorithms that would allow recovering the full trajectory of the camera. We use this actually to make drones safer than they are. So today, with the growth of autonomous commercial drones, there have been a few cases around the world where drones have lost at least a single motor and then they crashed. This actually is becoming a major concern. So the only way to prevent drones from crashing when a motor fails is to actually have a very accurate position accuracy. You can only do this with GPS. If you try to do this with the onboard cameras, the problem is that when a motor fails, if you look at my hands, the drone starts spinning on itself as a ballerina. So see what happens in this video. Here we induce the one motor to fail, and then the drone starts spinning on itself. Now, if you use a standard camera, which is the one on the left, well, a standard camera is affected by motion blur. On the other side, the event camera is not. So you can sustain a flight during this very high-speed spinning motion with the much darker environments that you could possibly do with the standard camera. And this research then inspired a collaboration with the Jet Propulsion Laboratory, and we just published a paper on exploring event cameras for future space missions, in particular for high-speed motion. Because when you fly very close to environments, especially in low-lit environments, then you have to take care of these problems. Now, if you look at the current research on event cameras compared to the past few years focused on using only event cameras alone. But now what is happening worldwide is that the community is actually focusing on combining event cameras with standard RGB cameras. Why? Well, event cameras have a very high temporal resolution, but low spatial resolution, while standard RGB cameras have resolutions up to, well, more than 40 megapixels and more. And so the idea is to combine the best of these two sensors. And you see here, so basically you have a high resolution frames, and then you have a high temporal resolution events that come in the blind time between two frames. And what could be possible applications? Well, what you see in this video is a CVPR paper we published this here, is where basically we take as input a low frame rate video, we combine it with the events in between two frames, and we output a high frame rate video. Also, other colleagues have also worked on trying to deblur these frames and so on. And what are the advantages of this? So by doing so, you can actually even achieve upsampling factors of 50. So you can upsample the low frame rate video by up to 50 times. But more importantly, you can cut the memory storage by a lot. We show in the paper up to 40 times. And that means that if before to take a slow motion video would take you 16 gigabytes per second, now it would take you only 0.5 gigabytes per second. And this is actually very promising also for low latency and low memory storage applications for advanced driving assistance systems and also VR and AR applications. We are also collaborating with Sony to investigate the combination of event cameras with projectors, laser projectors. At the moment, how do you do depth estimation using laser projectors? There is the so-called structural light framework, where basically you project a line and then you observe the deformation of this line on the surface of the object, and then by triangulation you obtain the depth. The problem with the standard image-based structured light is that you need to store a frame every time you move the line to a new position. This means that actually, if you're using a standard cameras, you have at least 1,000 lines that you need to actually collect for every single frame. While with an event camera, you can only focus on what changes. And so you can save the storage by at least 1,000 times and also reduce significantly the latency. So we have done that, and this is actually the final result. You can see, for example, that we are able to compute depth of very fast moving phenomena like ping pong balls, even a fan, and even an exploded balloon with very, very small latencies compared to current, for example, Kinect sensors. And finally, again, with Sony, we are exploring event-guided depth sensing, where the idea is to only illuminate with LiDAR the objects that move. Why would you need to do that? Well, currently, if you illuminate the scene for automotive applications with LiDAR, you basically are illuminating uniformly the entire scene. Event cameras instead would tell you what is moving. And so the idea would be to sample with the higher density objects that are moving, and with lower density objects that are not moving. And so we have a proof of concept that you see here, where my student is moving her arm, and you can see that basically the laser projector illuminates with higher spatial density the objects that are moving, and with lower spatial density the ones that are not moving. And what is the promise? Because event cameras usually react to only 10% of the scene, this technology promises to lower the power consumption of LiDAR by up to 90%. And so what are now the next challenges for event cameras, vision-based applications? Well, all these systems that you saw in these slides were running on standard CPUs or GPUs. So we still lack efficient algorithms that do not affect the final performance. But also they need tons of data for training. And at the moment, there is too few event camera data sets. And the question is, where can we find enough learning data? Thank you for your attention.
Thanks a lot, Davide. You have time for one quick question. Conventional AI already does frame rate upsampling quite well. Although training is energy heavy, application isn't. What would be the advantage of event-based methods?
So as I said, advantage would be that you cut the memory storage by a lot. So when you use a high-speed camera like a Phantom, you're basically storing all these thousands of frames per second. So if you use, for example, a Huawei phone, if for a slow motion video, they actually consume 16 gigabytes per second of video, while using events, you actually reduce much more the bandwidth. And so at least you can, for example, consume much less than 0.4 gigabytes per second of video.
Thanks, David.
Plus, you can also record a longer phenomena. At the moment, you can record like a few seconds. With an event camera, you can record actually minutes.
So I want to thank all of the speakers for providing such a clear and interactive overview of the field, the Technical Program Committee for putting this program together, and of course you for attending this event. So if you'd like to go beyond today's talks, you will find in the download section of this event's website a PDF file that contains one-page summaries of all the talks that you have seen today. And these also contain some useful references to go further.
This is the list of our strategic partners, starting with the executive ones: ARM, Edge Impulse, Qualcomm, Syngh, and we have DeepLight as a platinum sponsor, Clickertech, Platinum, Reality AI, Renaissance, Sony. Gold sponsors are Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SenseML, ST Microelectronics, Synaptics, SynSense, we presented today. And we have several strategic, silver strategic partners here. And just at the end, if you can go to tinyml.org website, and you're going to see a lot of events happening in this fall and in the next 6 months. Again, thank you again, and we'll stay in touch.